Okay, this is my Math Lab lesson 1.2, Symbols and Sets of Numbers. And we have three objectives today. First is to compare and order real numbers. Second is to identify sets or types of real numbers. And third is to represent integers from real-life situations. So let's look at some examples of comparing and ordering real numbers. The first thing I want you to understand is that all real numbers can be put on a number line. And a number line is just a line that extends infinitely in both directions, and we can place any number, any real number, on a number line. So in this first example here, we'll compare -3 to 2. Now we want to fill in the box with a mathematical symbol. And these are the 5 mathematical symbols that we have to choose from. And I want you to get them in your notes. Our first symbol is an arrow that points to the right. And that symbol means greater than. The next symbol is an arrow that points to the right with a line under it. And that symbol means greater than or equal to. The next symbol is an arrow that points to the left. That symbol means less than. An arrow that points to the left with a line under it means less than or equal to. And last, of course, we have the equal symbol. So in example 1, we want to put one of these mathematical symbols in the box between -3 and 2 to make the mathematical sentence true. If we use our number line to plot -3 and 2, we can kind of see which one is less or greater than. So -3 is here on our number line, and 2 is here on our number line. -3 is to the left of 2, so that means that -3 is less than 2. We always read these mathematical sentences from left to right, just like you would read a book. So -3 is less than 2. You could write that out in a sentence. So -3 is less than 2. That is a true statement. Looking at our next example, we're going to compare +3 to -2. Again, I'll start by plotting both of those on the number line. +3 is here, -2 is here. +3 is to the right of -2. That means that +3 is greater than -2. So I can put the symbol for greater than, because remember, I'm reading from left to right. Here's the sentence that goes with that. 3 is greater than -2. Taking a look at example 3, we're going to evaluate the following statement to be true or false. 2 plus 9 is greater than or equal to 2 times 9. In order to figure out if this statement is true or false, we need to work out both sides to get an answer before we can tell which side is has the bigger number. 2 plus 9 is 11, and 2 times 9 is 18. So is 11 greater than or equal to 18? The sentence that matches this mathematical statement is 11 is greater than or equal to 18. And that statement is false, because we know that 11 is really less than 18. Now, before we go on to other examples of comparing real numbers, we need to talk about another mathematical symbol called absolute value. I want you to get this down in your notes. Absolute value is the distance a number is from 0. The mathematical symbol for absolute value is 2 vertical lines around a number. So these 2 vertical lines that I've drawn around -7 indicate absolute value. So the absolute value of 7 is equal to 7. because if we drew a number line, -7 would be 7 units away from 0. 1, 2, 3, 4, 5, 6, 7. Distance can never be negative, so that's the reason absolute value will be a positive 7, because -7, the distance it is from 0, is 7 units. So again, we've got another absolute value here because I've got two vertical lines around the number 4, and this wants to know the absolute value of 4. How far is that number away from 0? Again, if we draw our number line and count, we can see that 4 is 1, 2, 3, 4 units away from 0. And again, it's a positive 4 because distance is a positive number. So don't think of absolute value as opposites. Absolute value is distance. How far is the number away from 0? So it will be a positive answer. -7 is 7 units away from 0, and 4 is 4 units away from 0. So looking at this other example that says determine whether the following statement is true or false. If false, give a counter example. That means if it's false, give an example that you know proves that that statement is wrong. So the statement is the absolute value of a negative number is always greater than the absolute value of a positive number. Choose the correct answer below. So if we thought that statement was true, we would just choose true. Now, before we do that, let's just go ahead and work out the other two false examples and see if this statement is true. So the absolute value of -3, we know to be 3. And then we have the less than sign, and the absolute value of 7 is 7. So the absolute value of this negative number is not greater than the absolute value of the positive number 7. So this is the right answer. Now if we go ahead and work out the next one, the absolute value of 7 is 7, but that's not less than 3. So this is not a true statement. So the first one is the correct one. So this statement is false because the absolute value of a negative number isn't always greater than the absolute value of a positive number. Okay, at this point I want you to work some problems on your own for comparing and ordering real numbers. And those problem numbers in your homework are problems 1 through 14 and 20 through 26. Okay, the next thing we want to do today is identify sets or types of real numbers. Now, there are two types of real numbers. First, there are rational numbers, and rational numbers can be written as a fraction. And then there are irrational numbers, which cannot be written as fractions. These are opposites of each other. So you have real numbers, and two types of those are rational numbers and irrational numbers. They can't be both because they're opposites of each other. Under rational numbers, there are 5 types of rational numbers. First, you have natural numbers. Those are the numbers you learned to count with when you started counting in preschool. You started with the number 1, 1, 2, 3, and so on. The second type of rational number is a whole number. Whole numbers are all the natural numbers plus 0. So 0, 1, 2, 3, and so on. Now notice that a number can be both a rational or a whole number and a natural number, which makes it a rational number and a real number also. So for instance, the number 3. The number 3 is a real number. It's a rational number because I can write it as a fraction, 3 over 1. It's a natural number and it's a whole number. The next type of rational number is an integer. Integers include positive and negative whole numbers. So -3, -2, -1, 0, 1, 2, 3, and so on. And notice that the dots go in either direction. So -4, -5 are also included all the way to infinity and back. Another type of rational number are repeating decimals. For instance, 0.3 repeating, 0.6 repeating, and 0.16 repeating. Lots of different repeating decimals. Those are rational numbers because I can write all of these repeating decimals as fractions. 0.3 repeating is 1/3. 0.6 repeating is 2/3. 0.16 repeating is 1/6. The last kind of rational number is a terminating decimal. Terminating decimals, for example, are like 0.5, 0.25, 0.2, etc. Those decimals that don't go on forever, they stop, they terminate. And these are rational numbers because I can write them as a fraction. 0.5 is the same as 1/2. 0.25 is the same as 1/4. 0.2 is the same as 1/5. Now, irrational numbers cannot be written as fractions. However, we can still put them or estimate them on a number line. All irrational numbers have to be rounded. They have to be estimated. The most common irrational numbers are pi. Pi is estimated to be approximately 3.14, but in truth, pi never ends and it never repeats. The scientists have never found an end or a repeating pattern to pi. So that's the reason it's irrational. We don't know how to write it as a fraction because it doesn't end, it doesn't repeat. Another common irrational number are square roots that aren't perfect. For example, the square root of 2. There's no number times itself that equals 2. So the square root of 2 is an irrational number. So you might think of real numbers as a Venn diagram. Again, for real numbers, we've got two types, rational and irrational numbers. In the rational numbers, we've got 5 different kinds. We've got natural and counting numbers, whole numbers, and integers. And natural and counting numbers are also whole numbers and integers. That's the reason the natural and counting numbers are inside of the circles for whole numbers and integers. And then you've also got repeating and terminating decimals that are rational numbers. Then irrational numbers, we've got 3 most common types are pi, square roots of non-perfect squares, and then never-ending decimals that have a pattern. So I've got the handout for you for the Venn diagram of real numbers, and this may help you categorize numbers into their proper place. So if we look at an example here, it says choose which group of sets the following number belongs to. Be sure to account for all sets. And they want us to choose where does -6 belong. So let's go to our Venn diagram and figure that out. So because -6 is a whole number, or a negative whole number, that means it belongs here in the integer circle. So I know that -6 is an integer. It's not a whole number because it's negative. It's not a natural number because it's negative. So it's just an integer. It's -6. But because it's an integer, that makes it a rational number. And all rational numbers are also real numbers. So we want to choose the choice that says integer, real number, and rational number. So the correct choice is choice A here, integer, rational number, and real number. Now if we were trying to choose where the number 6 belonged, not -6 but just +6, +6 would be a natural counting number. It would also be a whole number. It would also be an integer. And then that makes it a rational number and a real number. So a number can be several things, especially if it's a rational number. It can be in several of these circles. All natural numbers are also whole numbers and are also integers. Okay, at this point I want you to pause the video and work on problems 17 through 19 and 27 and 28 to test how you can do on identifying sets or types of real numbers. Our last objective today is to represent integers from real-life situations. Now remember, integers are positive and negative whole numbers. So what kinds of things in the real-life situations would be positive numbers, and what kinds of things would be negative numbers? Things like altitude are positive numbers. because that's how far up from the ground you are. A deposit is a positive number. Deposit is how much money you put into the bank. The number of yards gained in a football game would be a positive number. Below sea level would indicate a negative number. That's how far below the ground you are. A withdrawal is another negative number. That's money you take out of the bank. And yards lost is another negative number. If you lose yards in a football game, that's a negative number. So for instance, in this example, a mountain has an altitude of 544 feet and land lies 6 feet below sea level. The integer 544, positive 544, represents the mountain's altitude. The integer -6 represents the land level with respect to sea level measured in feet, because below sea level means it's got to be negative. In the next one, John Appleby deposited $270 in his savings account. He later withdrew $1. The integer that represents the amount he deposited is a positive 270. The integer that represents the amount that he withdrew is -$1, because a withdrawal is a negative number. That's all the examples for this lesson. To finish up your homework, you can do problems 15 and 16 and test your skills at representing integers from real life situations.